So, welcome back to the course on blockchain. So, in the last class we are looking into the permission blockchain settings, and in the context of permission blockchain the concept of state machine replication, which will help you to achieve a consensus in a permission model. So, in the last class we are looking into this concept of state machine replication, where we have seen that you do not need to execute a smart contract to all the nodes. Rather, you can execute it on a subset of nodes, and then you can ensure that the state of the contract is getting propagated to all the nodes in the network, and there are certain consensus mechanism which will ensure you that the states which have been propagated by multiple state machines or the contract executor, they are indeed on the same page or they are indeed correct. So, by applying this kind of distributed state machine replication technology, you can ensure consensus in a permission blockchain environment. So, let us look into that, what is meant by a state machine replication. So, a state machine can be characterized by a set of parameters. So, the set of parameters are a set of states based on the system design. So, here in this particular example you have 3 states S1, S2 and S3. Then you have a set of inputs which will tell you about how your system will behave. So, here are 2 inputs, 0 can be one input to the system and 1 can be another input to the system. Then you have a set of outputs. So, here S3 is the final output of the system that is represented by the state machine. A transition function. So, the transition function will take a state and then input as its input, and it will produce a set as the output. So, here from state S1, if you take 0 as an input, it produces state S2 as the output. So, this is a transition function. Then you have a output function which may produce the output of the system. So, this particular example we do not have any output, but it may happen that if you have S1 and input as 0, you are moving to state S2, that is your transition function, and at the same time you may producing as output 0. So, that way for certain state machines you may have a output function, and there would be a designated start state. So, here S1 is denoted as the start state of the system. Now, any algorithm, any finite state machine which represents an algorithm, that can be represented using a finite state machine. So, let us look into one example where you can represent a smart contract as a state machine. So, earlier we were talking about this kind of crowdfunding platform. So, in a crowdfunding platform you have a set of set of people who have certain funds available, who are agreed to donate the fund if certain jobs are being done. So, there are the project proposals which are coming from the proposers. So, the proposer propose certain jobs, certain projects, and if certain funding agencies or funders, they find that particular proposal interesting, they may fund for the proposal in a collective way. So, that is a kind of crowdfunding platform like a Kickstarter, which example we have looked some time back. So, let us look into that, how we can represent a crowdfunding application in the form of a state machine. So, here the system has an initiation state where some users, they have submitted certain proposal. Now, that proposal, once someone likes this proposal, they may transfer the money. So, here say Bob has transferred the committed money to the system. So, you are reaching to a state that Bob has donated the money. Similarly, if Alice has transferred the committed money, you are reaching a state that Alice has donated the money. Now, after Bob has donated the money, Alice may donate the money after that, or it may happen that Alice has first donated the money and after that Bob has donated the money. Now, when both of them has donated the money, either in the order of Bob Alice or Alice Bob, you have the money available in the system. Now, once you have the money available in the system, you can initiate the job and say there are 2 jobs that need to be executed, but there is no specific sequence in which the jobs need to be executed. So, it may happen that the job 1 is first complete and then the job 2 is complete. So, then you follow this path to make both job 1 and job 2 complete, or it may happen that the job 2 first get finished, after that job 1 is get finished. So, in this particular order you may again have this job 1 and job 2 get complete. So, once both the job done, then your smart contract will transfer the money from the funders, which are here the Bob and Alice, to the project proposal. Say if Eve has transferred that project proposal, the money will be transferred to Eve. So, that way you can represent a smart contract in the form of a state machine. Indeed, any algorithm you can represent it in the form of a finite state machine. Now, in a typical distributed architecture, the distributed state machine replication mechanism works in this way. So, you have multiple servers which works in a distributed fashion. So, the advantage of using distributed servers in place of a centralized server that we discussed earlier. So, the idea is that first you have multiple servers here. So, you place the copies of the state machine on each of these server. So, each of these server has a copy of this entire state machine. Then servers get the client request. So, here it is like that Bob is submitting his request and Alice is submitting her request, and the request goes to different servers. Now, when the requests are going to the different servers, so if you execute the state independently at each server, the state that will be there in this server and the state that will be there in this server, they may be different. So, here you will reach to a state that Bob has transferred the money, here you have reached the state that Alice has transferred the money, but collectively you have to ensure that all the 3 server reaches to a state after certain time that both Bob and Alice has transferred their share of the money. So, to achieve this, the state machine replication mechanism works in this principle that you propagate these inputs to all the servers. So, all the servers has the input like that Bob has transferred the money and Alice has transferred the money. Then you order the inputs based on certain ordering algorithm. You can have an associated timestamp with every individual transaction. So, whenever Bob is making his transaction, it is associated with a timestamp, and when Alice is transferring her share of money, that particular transaction is associated with another timestamp. So, based on that timestamp, you can have an ordering of the transactions, and then once this ordering is done, then every individual system they execute the inputs based on the orders which have been decided, and they execute it individually at each server. Now, once this information is executed in each server in that particular ordering algorithm, then you know that well, first the transaction corresponds to Bob, that will get executed, then the transaction corresponds to Alice, that will get executed, and all the servers reaching to the same state that both Bob and Alice has transferred their share of the money. Once this transactions is done, then sync the state machines across all the servers to avoid any failure. It may happen that this server during the say this server during the execution it has failed, and after some time it recovers. So, once it recovers, it should get this updated state that well, both Bob and Alice has transferred their share of the money. So, that update is done through synchronization of the state machine. Now, here in this entire algorithm, we have certain outputs that can be produced, like it may happen that well, the output is when both the share of the money has been transferred, you send the output or you notify the client that well, the job is now ready to get executed. So, that particular output is sent from the server to the individual users. Now, in this entire procedure, there are 2 glitches. The first one is that you need to maintain an ordering service, and the second is that in the presence of a failure, you need to ensure that all the individual servers are in the same page. Everyone knows that well, both the transactions from Bob and Alice, they got executed and the entire money has been transferred. Now, to ensure that, you need to have a kind of consensus algorithm in the system. Now, why do we apply this kind of state machine replication based consensus algorithm in a permission model in contrast to the challenge response based consensus model which we applied for the permissionless setting. So, there is certain natural reasons to use state machine based consensus algorithms over permission blockchain. So, the first reason is that the network is closed. So, when the network is closed, every individual nodes they know each other. So, state replication is possible among the known nodes. So, if you know that who are your peers, you can always replicate your state machine with the current state to your peers. The second thing is that this particular state machine replication based scenario, it avoids the overhead of mining. So, mining has a significant overhead in terms of the system power that you are using, in terms of the time that you are providing, and the amount of Bitcoin that you are you may apply for this kind of proof of stake based mechanism. Or proof of elapsed time based mechanism. So, it is like that either in case of a challenge response based method, either you have to spend your physical assets or you have to spend your digital assets, and it will take certain time to solve that particular challenge. So, that has significant kind of overhead in case of a permissionless setting, but in case of a permission model, because we know the participant each other, and in case of a state machine replication, you do not have this kind of overhead where you have to spend your physical asset or some kind of virtual assets. Rather, what you have to do that you have to imply certain kind of message passing algorithm in the system. So, you can avoid the overhead of mining by applying this kind of state machine replication based method, but as I have mentioned that consensus is still required on top of this state machine replication, because the machines can be faulty or they can behave maliciously. So, let us quickly go through the consensus algorithms. So, earlier we have looked into this concept of distributed consensus. So, in case of a consensus algorithm, well, if there is only single decision maker, you do not require any consensus. Whenever there are multiple decision makers and in a collective way they want to come to certain decision, then you require the consensus. So, the distributed consensus, it helps you to reach in an agreement in case of a distributed computing. So, in terms of the state machine replication concept, you replicate the common state, so that all the processes they have the same view of the state, they can understand. So, if I just draw a simple state machine that so this particular graph can give you a simple state machine and say this is the final output state, this is the initial state, and there are say individual inputs, and from here the system reaches to the state. Now, it may happen that the system has reached to some intermediate state, say the system has reached up to this state. If the system has reached up to this state, then you need to ensure that all the processes, all the users who are there in the system, they have the same view, they get the same view that the system has reached to this particular rate state. Now, there are multiple applications, like one typical application of this state machine replication is the flight control system. When there are multiple flights and they want to coordinate their positions among themselves, you can apply this kind of state machine replication technique in distributed system to achieve consensus. Then for fund transferring system in a distributed environment, like for the cryptocurrencies, we are going to see that, well, in a closed environment you can apply state machine replication based algorithm for consensus. In a open environment, we have looked into that, well, you can have a challenge response based consensus algorithm to achieve the consensus. Then for certain other distributed applications like a distributed leader election, where all the nodes collectively need to elect one leader in the system, for that kind of applications you have to ensure certain kind of consensus that all the nodes elect the same leader, or the same leader is elected at the end of the route. For this kind of agreement protocols, where the nodes collectively needs to come to certain agreement, we require this kind of distributed consensus algorithms. Well, we have looked into that we do not need a consensus in a single node process, but when there are two nodes. So, in case of two nodes, if there is kind of fault, if the network is fault, or even if there is a kind of crash fault, even if the node behaves maliciously, you cannot reach consensus. To reach consensus, you always require more than two nodes. Now, these things we have looked details earlier in the context of permissionless blockchain, that in a distributed environment you can have primarily three types of fault. The first fault is the crash fault, where a node crashes and is not able to send any message. So, it may recover after some time and it may start sending the message again. So, this we call as a fail stop behavior. Then you can have the network or the partition fault, where because of a network fault that entire network gets partitioned and the message from one partition is not able to get propagated to another partition. The third type of fault, which is difficult to handle in a distributed environment, is a Byzantine fault. So, you have kind of malicious behaviors among the nodes, which may come due to certain kind of hardware faults or software faults. So, this Byzantine fault is that for certain views the node is behaving in one way, whereas for certain other views the node is behaving in a different way. So, to reach the consensus for three process, so every process can have in one of the three states. One is the undecided state. In the undecided state, the process or the node has proposed certain value from a set of feasible values D. So, every node has proposed some value and they are in the undecided state. Then in the communication state, they are exchanging the value among themselves. So, by exchanging the value and then by applying the consensus algorithm, so they can reach to the decided state, where they set the decision that everyone in the network they agrees on the variable say di, certain variable di. So, there are certain requirements of a consensus algorithm, the details you have looked earlier. So, you need to ensure that eventually each process sets the decision variable. So, it terminates after setting the decision variable. Then the agreement property, which says that the decision value for all correct process that should be same, everyone should reach to the common agreement. The third one is integrity, that if the correct processes all propose the same value, then any correct process in the decided state they have chosen that value. So, if every correct process propose one value x, so at the decided state they should decide on that same value x. Then we have different kind of algorithms for ensuring consensus in a typical distributed system, which we apply in permission blockchain, and these algorithms are based on this state machine replication principle. So, their initial algorithms for distributed consensus are Praxis and Raft, which support crash or network faults, but they cannot support Byzantine fault. So, to support Byzantine fault, we have algorithms like Byzantine fault tolerant algorithm or practical Byzantine fault tolerant or PBFT algorithms. So, this Byzantine fault tolerance algorithm they support Byzantine faults in addition with the crash or network fault. So, initially we will look into this Praxis Raft in details and then we will go to the Byzantine fault tolerant algorithm. So, let us go to the Praxis. So, Praxis has an interesting history. It was the first consensus algorithm that was proposed by Leslie Lamport in 1989, and the objective of Praxis was to choose a single value under a crash or network fault. This Praxis, although it was proposed by Lamport in 1989, but it took around 13 years to get the paper published, and there was a lot of discussion among the community about the correctness of this particular algorithm. So, the reviewers are not very convinced that the algorithm proposed by Lamport is fair enough to ensure consensus in a distributed environment, and Lamport tried to come up with a formal proof of this particular consensus algorithm. And because of that complicated proof, people say that well, it is very hard to understand the Praxis algorithm, or it is very hard to implement the Praxis algorithm. But although the inherent concept of Praxis is kind of very simple. So, we will look into the Praxis in a simplified view, and then we will see that how Praxis can be implemented in a real system to ensure consensus. So, the idea behind Praxis is pretty simple. It is like that. I am just giving you one example. So, in IIT Kharagpur, we have broadly two options where the student can go, say after a class, say we have a subway and we have a CCD. Now, after the class, the students can collectively decide that all of them want to go for either for the subway or for the CCD. Now, the question comes that how will they select that whether they want to go to CCD and go to subway. And the interesting is that all of them want to go for together, otherwise the party would not be that much good. So, that is why the students want to make some decision collectively that they want to go to either subway or CCD, but there is no central leader. The only way to communicate with that, they will just everyone will propose certain values, and from that value proposal they will try to come to a consensus. So, the idea is something like that. Say assume that I am a member of that particular team of students. Now, I just wait for some amount of time and I see that whether someone else is proposing a value to go for a CCD or to go for a subway. If none of my friends are proposing any value, then I initiate a proposal. Say I initiate a proposal, say that let us go for subway. So, now I will see whether my friends are accepting that value or not. So, that way the information gets propagated in the entire network and they try to have to some certain consensus based on a majority decision that well, if the majority of the nodes proposes that or either proposes or agrees that we want to go to subway, then all of them goes to for subway. Otherwise, if majority of the students propose to go for CCD, then all of them go to CCD. So, that is the broad idea behind Praxis. So, let us look into that algorithmically how it works. So, you have certain proposers who are proposing the values. That proposed values should be chosen by the consensus algorithm. So, here the proposers can propose a value that either to go for a subway or to go for a CCD. Then you have certain acceptors, they form the consensus and accept the values. So, the acceptors whenever they are hearing certain proposal from the proposers, they either accept it or reject it. Say it may happen that if I am willing to go for a subway, but some proposal is coming to me to go to CCD, I will simply reject it. And some other friend of mine, if he or she is proposing to go for subway, I will agree to that. So, that way we will try to look into that whether the majority of the node is either proposing or accepting this going for subway or CCD to which one, and accordingly this learner module will find out that which value has been chosen by each of these acceptor, and then they will collectively accept that particular value. So, that is the broad idea behind Praxis. So, there are these three type of nodes: the proposer, the acceptors and the learner. Everyone is a learner in the network which learns that what is the majority decision there. So, let us look into the process in a little detail. So, the proposer initially it prepare with a proposal number. So, this proposal number need to be good enough so that your proposal gets accepted. So, the proposal prepare that proposal number and send it to the acceptor. So, this proposal number it forms a timeline, and the biggest number it is considered up to date. So, it is like that one proposal is coming from P1 with proposal number say 100, another proposal is coming from say P4 with proposal number 102, then we will accept the proposal which is coming from P4. Then the acceptor makes it in this way, the algorithm that I have mentioned, that if the proposal number is less than the acceptorized proposal number. So, if you receive the lower proposal number, if your current proposal number is lower than the proposal number that you have, then you accept it, otherwise you decline it. So, each acceptor it compares the received proposal number with the current known values for all the proposers prepare message, and if you are getting a higher number then you accept it, otherwise you decline it. So, then the acceptor based on that it prepare the response. In the response the acceptor can either accept or decline a message based on the proposal algorithm. So, as I have mentioned that the biggest number the acceptor that has seen till now, it put that number in the response message, and it include the accepted values that has been accepted from the proposer. So, this accepted values is informed to the proposer. Now, we take a vote based on a majority decision. So, we see that well the proposal looks that whether majority of the acceptors they reject the proposal. If they have rejected the proposal, then you update it with the latest proposal number. If they have not rejected it, then you see that whether the majority of the acceptors have accepted the value. If the majority of the acceptor has accepted the value, then you cannot choose that particular proposal. If it is not, then you send a accept message. So, the idea is that whenever the majority of the acceptors they are sending some accepted values, if they have accepted your value, then that means the value that you have shared that is coming to be a consensus. So, it is just like that you have proposed for a pizza, you have proposed for a subway, and once you have proposed for a subway and majority of your friends have accepted for that subway, and from that vote you can all of you can go for subway. So, the final stage is this accept message. So, the proposer sends the accept message to all the acceptors. In the accept message you include the proposal number, similar to the prepare phase, that the proposer knows that my proposal has been accepted, and the value is the single value that is proposed by the proposer. Now, whenever the acceptor it accepts values from the proposer, it informs the learner about this majority voted value. So, everyone learns that what is the majority voting in the environment. Well, if you have a single proposal in the system, then the system is very simple. With a single proposal, every acceptor will accept that proposal because that is going to be the biggest, and so the proposal does not get rejected if the acceptors are correct. So, you have to ensure that if you need to ensure that majority of the acceptors are non-faulty. Now, let us see that whenever certain acceptor fails, so this acceptor can fail during the prepare phase. If the acceptor fails during the prepare phase, then you do not have any issue, that there are other acceptors who can hear the proposal and they can vote either for the proposal or against the proposal. Now, the acceptor may fail during the accept stage. Again, if the acceptor fails during the accept stage, you do not have any issue, because other acceptors are there who have already voted for the proposal. Now, the only thing that you have to ensure that less number of n by 2 number of acceptors they can fail simultaneously, because you are going for the majority voting principle. So, whenever you are going for the majority voting principle in a synchronous environment, you need to ensure that well, majority of the nodes are correct. So, if more than n by 2 number of acceptors fail, then no proposer they get a reply, and you cannot come to a consensus algorithm. Now, let us look into the scenario when a proposer fails. Now, the proposer can again fail during the prepare phase or during the say accept phase. So, if the proposer fails during the prepare phase, it is just like that no one is proposing for any value, none of your friends are proposing for either to go for a subway or to go for a CCD. So, you wait for getting a value from your friend, and if you are not getting any value, so you become a proposer. So, the same idea is like that the acceptors wait for certain times, and if they do not hear for any proposal, one of the acceptor it becomes the proposer and propose a new value. Now, the proposal may fail during the accept phase, but if the proposer fails during the accept phase, the acceptors they have already agreed upon whether to choose or not to choose the proposal based on the majority vote. So, they have shared the majority vote among themselves, and from there they can find out that whether the proposal has been accepted or not. Now, there can be an interesting attack here which we call as the dueling proposal. Say there are two proposals here. It is just like that the proposer 1 it has sent certain proposal to all the acceptor, and then proposer 2 it sends another proposal with a higher proposal number. Now, assume that proposer 1 she is an attacker, and what she does that the moment he sees there is a proposal with a higher proposal number, she sends another proposal based on a more higher proposal number. So, it is like that whenever she hears that well proposer 2 has sent a proposal with proposal number 201, she sends another proposal with 301. So, that way by applying the by having there can be a kind of dueling among the individual proposer, and you may not be reached to a consensus. Now, to break the tie here, what we do that we use certain other numbers or certain other identities which will help me to break the duel. So, it is just like that whenever you are getting dueling proposals, you block the proposer who are having lower IDs. So, you may break the ties based on the ID of the proposers. So, to do this, that which particular proposer you are going to block, you need to execute certain algorithms. So, you can have leader election algorithm. So, this leader election algorithm can select one of the proposer as a leader. Now, you can see that because Praxis is a consensus algorithm, Praxis itself can be used as a leader election algorithm. So, the view of Praxis that I have mentioned to you, it is a kind of very simplified view. The overall idea is that the proposer is proposing certain views to all the acceptors, and the acceptors they collectively look into that proposal, and if they agree with the proposal, they send the accept message, and by receiving that particular accept message, if the proposer finds out that his message has been accepted, then he sends back the accept to all other acceptors, and from there through the majority voting they come to a consensus protocol. Now, this simple view of the Praxis is easier to understand. It is just like making one selection, but if you look into the real system, in a real system you may go for a sequence of selection, sequence of choices rather than having a single choice. So, that kind of system we call it as a multi-Praxis system. So, this multi-Praxis system, it is something like this, you make a sequence of choices by applying repeated Praxis protocol. Now, applying repeated Praxis is something complicated because you have all these messages need to be exchanged among each other again and again, and which increases the complexity of the Praxis protocol. So, that is why although Praxis gives a nice theoretical idea about why the system can reach to a consensus or how a distributed system can reach to a consensus, indeed this Praxis protocol was the first that has proved that well you can have certain consensus algorithm in a distributed environment. So, by applying this kind of proposal and acceptors accepting certain values, so you can do certain level of optimizations on top of this repeated Praxis, which is basically done in case of multi-Praxis to come to a consensus. So, we will not go to the multi-Praxis in details, rather we will go for a simplified, more simplified consensus algorithm, which is widely adopted as an alternate of Praxis, which we call as a raft. So, in the next class we will look into the raft consensus mechanism in details. So, thank you all for attending. We will look into raft in details.